Evil Wifi is a weird character. She possesses people and is one of the few characters that aren't directly involved in any competition. But one of her most well-known features, for people that have read the title of this video, is the fact that she moves discreetly. But what does that mean? Things in the real world, and also most characters in BFDI, move continuously. So the position as time t is very close to the position as time t plus epsilon, where epsilon is an arbitrarily small number. So, to get from point A to a different point B, the path passes through an infinite number of points. But Evil Wifi doesn't move like this. Instead, she teleports, passing through a finite number of points to get from two points A and B that are separated by a finite distance. But in the real world, discrete motion is impossible. If you apply a force to an object, its acceleration changes. When you stop, the velocity is constant. So it's impossible to make an object teleport or move discretely in the real world. How are we going to explain evil Wi-Fi's movement? Force in the real world has units of mass times length divided by time squared, which can be written as mass times length times time to the minus 2. So applying 1 unit of force on an object with 1 unit of mass means that the object has an acceleration of 1. So each unit of time, the object gains 1 unit of velocity. An object moves at 1 unit of velocity when it moves 1 unit of distance each unit of time. So both velocity and acceleration take time into account to move the object. We need to wait some amount of time so that the object moves some distance. We need to remove the time component to enable discrete movement. In terms of units, it's simple. We just need to multiply force by time squared, and we get a quantity with units of mass times distance. So we remove the time component. We can also multiply force by time to get a quantity with units of mass times distance divided by time, which directly changes the velocity, or by time to the power of any integer. I am going to name these quantities forces of order n, represented by f subscript n, where n is the negative of the exponent that time is raised to in the unit. The force of order n has units of mass times distance times time to the minus n. Multiplying a force of order n by time gives a force of order n minus 1. One thing to note is that the momentum has the same units as a force of order 1, mass times distance times time to the minus 1. There are also some quantities that have the same units as a force of some order. I'm still calling these forces even though nothing is actually applying a force on the object, because usually this distinction isn't important. If this distinction is important, if a force is being applied on the object, it is called an applied force. And if it's the motion that the object gained from a force, it's called the motion force. A force of order n directly affects the motion force of order n, and they have the same units. For example, if I apply a force of order 2 of 10 newtons on an object, that object has a motion force of 10 newtons. So it has an acceleration of 10 divided by m meters per second squared, where m is the mass of the object. There is another thing we need to address: energy. If an object moves, the work of a force applied to that object is force times displacement, the distance moved, times the cosine of the angle between the force and the object's movement, although the angle part isn't important here. There is also a relation to power. Power equals force times velocity. Since we have forces with different units, the equivalent to power and energy changed based on the order of the force we consider, so it's useful to consider the order of energies. Order 3 energy or power has units of mass times distance squared times time to the minus 3, while order 2 energy, which is just energy in the real world, has units of mass times distance squared times time to the minus 2. Like with forces, the order of an energy is the negative of the exponent that time is raised to in the unit. If you multiply a force of order n by displacement, you get an energy of order n. If you instead multiply a force of order n by velocity, you get an energy of order n plus 1. Okay, so we have these equations, but what do they mean? Imagine we have two stationary objects with mass m and the same initial position. We apply a force of order 2 of 1 kilogram meter per second squared for 10 seconds on one object, and a force of order 1 of 10 kilograms meter per second on the other. We see that by Fn times delta t equals Fn minus 1, that applying the order 2 force for 10 seconds is equivalent to the order 1 force. As we see in this graph, the position of the two objects is different, but their velocity is the same. This is the case when the two objects have the same mass, but even if the two objects have different mass, their momentum is the same. More generally, the motion force obtained by applying a force of order n and intensity Fn on an object for some time delta t is given by Fn times delta t equals Fn minus 1. But what happens when the order 2 force changes? Let's say the intensity of the order 2 force at time t is given by F2 equals t. What is the order 1 force after time t? We can start by plotting the function ft equals t on a graph, which gives us a straight line. The force of order 1 at time t is the area below the line between 0 and t. In this case, the area is a triangle with base t and height t, so the area under the graph and the force of order 1 are t squared divided by 2. Let's now calculate the function for the order 0 force. We just need to find the area under the graph between 0 and t, just like before. But we have a problem. Before, the area we wanted to calculate was a triangle, which has a nice area formula. But here, we need to find the area under a parabola. So what is the area? To find the area, we need to use integrals from calculus. If you don't know calculus, I recommend the Essence of Calculus series by Triple Brown. Integrating t squared divided by 2 with respect to t gives t cubed divided by 6 plus c, where c is the initial position. You can also use the derivatives to go backwards. For example, the derivative of t cubed divided by 6 is t squared divided by 2 and its derivative is t. This process also applies to energies. You can find the change in order 2 energy by integrating the order 3 energy with respect to time, and use derivatives to go back. This leads to the final equations I want to put in this video, which are these equations where Ti is the initial time and Tf is the final time considered, and Fn of t and En of t are respectively the force and energy of order n at time t. In summary, the concepts of force and energy can be generalized to have different exponents in the time component. This not only allows for discrete movement, but also instantaneous changes in velocity. And although I haven't checked, I think that is very likely that there are some scenes where something gains velocity immediately, while forces with orders that are not between 0 and 2 and energies with orders that are not between 0 and 3 weren't discussed in this video. My theory still supports them, including negative orders, I think, and they could be useful to explain something later. This is all I have for this video. Goodbye.